Okay. Lesson 4.2, L'Hopital's rule. So back when we first started calculus, we were looking at limits, right? So what does this function approach? Or as we get closer and closer to an x value, what's our y value? And to do that, we would just plug in the value, right? Whatever the limit was approaching. Well, not all limits can be found that way, okay? So if when we do that direct substitution, it produces one of these two intermediate forms. So 0 over 0 or infinity over infinity. Okay, the signs have to match here on those infinities. Okay, let's make a little note there. Okay, so if we go through, we plug in those values into our limit, then we get that 0 over 0 or infinity over infinity. Then we can use L'Hopital's rule to help us find that limit. And L'Hopital's rule says if the limit as x approaches c of f of x equals 0 and the limit as x approaches c of g of x equals 0, or if both of these limits are plus or minus infinity, then the limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f prime of x over g prime of x. So that says that if we get this interdeterminate form, right, the 0 over 0, infinity over infinity, then we can go through and take the derivatives of our two separate expressions and then take the limit again, okay? And it says to use L'Hopital's rule, you need the limit of an expression written in a fractional form. So we need a numerator and a denominator. So let's look at our first example. We have the limit as x approaches infinity of x over e to the x, okay? So kind of ultimately in our heads, we want to kind of think, what's this going to happen, okay? So the limit as x approaches infinity of x is going to go towards infinity. Plug it in. Okay, so that one's infinity. And the limit of x as x approaches infinity of e to the x, well, it's e to the power of infinity, is going to go towards infinity. So ultimately, we're going to get infinity over infinity. So we're going to need to use L'Hopital's rule. But to do that, essentially, we need to state those values. So here, I'm going to go through, and this is me essentially saying that I can use L'Hopital. So the limit as x approaches infinity of x is equal to infinity, right? We just said that. And the limit as x approaches infinity of e to the x is also infinity. Okay, so that's essentially me like stating, yay, we can use this, right? Like that's my justification, okay? So because that's true, we can then go through and look at our limit again. Notice I'm writing out what we started with, okay? And it's not equal to that first line I wrote. It's not that limit that we started with. The limit as x approaches infinity of x over e to the x is not equal to these two separate pieces that I wrote, okay? So we're rewriting the beginning is equal to, now we're going to do our limit as x approaches infinity, and we're going to take the derivatives here. Okay, so the derivative of x is 1. Okay, make a little note here, okay. Right, so dx of x equals 1, okay, over, and then our derivative of e to the x is still e to the x. So now we're going to look at the limit as x approaches infinity of 1 over e to the x. Okay, When I plug infinity into here, I get 1 over essentially infinity, which makes this a really small number. So as our function, okay, here, our x over e to the x, the closer and closer it gets to infinity, the closer that y value gets to 0. Okay. So now let's look at number 2. Okay, number 2, I've got the limit as x approaches infinity of e to the x over x. Okay, once again, kind of a in my head kind of thought process, right? If I plug in infinity, I'm going to get infinity over infinity again. So we're going to need to use L'Hopital's rule. Okay, so we're going to state each of the little pieces. So the limit as x approaches infinity of e to the x. That's infinity. And the limit as x approaches infinity of x also equals our infinity. Okay, so now we can apply L'Hopital's because it meets that condition. If both of our limits of our numerator and denominator are equal to the same either 0 or infinity, then a little bit. The limit as x approaches infinity of e to the x over x is equal to the limit as x approaches infinity. Derivative of e to the x, derivative of x, 1. So we get the limit as x approaches infinity of e to the x. Right? When I plug in an infinity here, we get infinity. Okay, let's look at our third example here. Number 3 says the limit as x approaches 0 of x over e to the x. Okay, right? We're gonna look and think out loud. Right? The limit as x approaches 0 of x, that's just going to be 0. The limit as x approaches 0 of e to the x, anything to the 0 power is 1. So ultimately, we're going to get 0 over 1, which gives us 0. Okay. So number 3, even though it looks like problem 1 and 2 that we just did, it doesn't get that indeterminate form. Okay. So you do have to kind of keep an eye on it, kind of for these lookalikes. Okay. Ooh, that went bad. Oh, there we go. So not indeterminate. We just take the plug in the values, go from there. Okay, let's look at number 4. Number 4, I've got the limit as x approaches 0 of 3 minus 3e to the 3x over x. Okay. Right, kind of just what happens if I do plug in 0. On the top, if I do 3 minus 3e to the 3 times 0, well, that gives me e to the 0. Okay, and I'm going to write out in pink, just kind of so I can show you my thought here. Right, this isn't what I'm writing to do my problem necessarily. Right, so my thought is if I do 3 minus 3 e to the 3 times 0, right, then this whole e to the 3 to the 0 power, that's really 1. So I really get 3 minus 3, so that's going to be 0, right? And I know that the limit as x approaches 0 of x is also 0. So we are going to have L'Hopital's happening here. So we're going to write out essentially our justification. So the limit as x approaches 0, 3 minus 3 e to the 3x is equal to 0. And the limit as x approaches 0 of x also equals that 0. So because that is true, then we can look at our limit again. So the limit as x approaches 0 of 3 minus 3e to the 3x over x is equal to the limit as x approaches 0. Okay. Denominator is really easy to take my derivative. It's just 1. Okay. Numerator, I have 3 minus 3e to the 3x. Okay. So the 3 out front, that's all by itself, no variables. That's a constant. Its derivative is 0. Okay. So then I'm going to have a negative 3e to the 3x. So we're looking at, well, this is really a chain rule, okay, because I've got this e to the 3x. Okay. So I'm going to use my purple and kind of show what we're doing here, right? So that 3 minus 3e to the 3x, right? I said that when I take my derivative, that 3 out front becomes a 0, and then I'll have, okay, the minus 3 sits there. Derivative of e to the u, right, that substitution idea, is still e to the 3x, and then we have to take the derivative of the inside, so times 3. So I'm left with a negative 3e to the 3x times 3, which is going to give me negative 9e to the 3x. Okay. Go through, and if I plug in 0 now, I'm going to get negative 9, because e to the 3x, right? When I plug in 0 for that, I get e to the 0, which is 1, so we get negative 9. Okay. Next, number 5, it says without our L'Hopital's rule. Okay, so we're going to look at this. Right, if I plug in negative 1 in this case, I'm going to get 0 on the bottom, in the denominator, right? Which we're going to have. So what I'm going to do is I'm first going to factor this. So the limit as x approaches negative 1. I've got 2x squared minus 2, so I can factor out a 2 first and get 2 times x squared minus 1 all over x plus 1. Okay. Put a little equals there. Okay. And then I'm going to factor that difference of squares. So x squared minus 1 becomes x plus 1 times x minus 1 all over x plus 1. Okay. Divide out like terms. So we're left with the limit as x approaches negative 1 of 2 times x minus 1. Okay, now if I plug in negative 1, I get 2 times negative 1 minus 1. So I get 2 times negative 2. So we get negative 4. Okay. And we'll make a note here that we factored. Okay, next, 6 is the same limit, but this time we're going to see if we can apply L'Hopital's rule instead. So the limit as x approaches negative 1, right? We already know that that denominator, if I plug in negative 1, I get 0. So let's kind of think about that numerator. Okay, well, if I plug in negative 1, I'm going to get 2 times negative 1 squared. So that's going to be 2 times 1, so 2. And 2 minus 2 is 0. So looks like it will work out. So the limit as x approaches negative 1 of 2x squared minus 2 is equal to 0. And the limit as x approaches -1 of x plus 1 also equals 0. Actually, yeah, okay. So the limit as x approaches -1 of 2x squared minus 2 all over x plus 1 is going to equal the limit as x approaches -1. Take the derivative. So I've got x squared. So that means I'm going to then drop the 2 in front. So we have 2 times 2 is 4x over x plus 1. Take that derivative. And we just get 1. Okay, so now we're looking at the limit as x approaches -1 of 4x. So plug in our -1 and I get -4. Right? Same exact problem from 5, same exact answer, right? But ultimately, I just was able to take those derivatives. Okay, so right, it says do not use L'Hopital's rule just because a problem looks like a candidate for the rule, right? Number 3 was our example. Okay. Also, sometimes we use L'Hopital's rule. Everything, right? Like, set it up, say, like, yes, they both reach that indeterminate form. And then from there, we take our derivative, everything. And then when we go to take the limit again, we get another indeterminate form. Okay? It can happen. It works. Okay? We just need to make sure we keep stating kind of those indeterminate forms. So let's look at example 7. I've got the limit as x approaches -infinity of x squared over e to the -x. Okay. So thought process, right? If I plug in -infinity to x squared, anything squared is positive, so I'll get positive infinity. If I plug in -infinity to e to the -x, well, a negative times a negative is positive. E to the infinity, still infinity. Okay, so we're going to get infinite for both of them. So we're going to write it out. X equals, or as x approaches -infinity of x squared, right? We said that was infinity. We also said that the limit as x approaches -infinity of e to the -x equals infinity. So we're going to take our derivatives. So the limit as x approaches -infinity of x squared over e to the -x is equal to the limit as x approaches -infinity. Okay, take the derivative. So x squared's derivative is 2x. E to the -x is going to be -e to the -x, right? It is that chain rule still with that -x in there. Okay. Now when I think about it, right, if I plug in -infinity, I'm going to get essentially 2 times -infinity, so -infinity. And in the denominator, I have -e to the -x, so -e to the -infinity, which turns into a positive. So then I still get a negative because of the negative chilling out front. So we hit that indeterminate form again. Okay, so we're going to write here again that the limit as x approaches -infinity of 2x equals -infinity. And the limit as x approaches -infinity of -e to the -x also equals -infinity. Okay, I'm just going to write out here in pink so you can see, right? Like 2 times infinity, -infinity equals -infinity. And -e to the negative infinity, negative e to the positive infinity, which is going to give us negative infinity. Just so you can see my little kind of work there. Okay, I'm going to pull these down a little bit further. Okay, so now that we've shown that, we're going to take and use that L'Hopital's rule again. So we can say that the limit as x approaches negative infinity of 2x over negative e to the negative x is equal to the limit as x approaches negative infinity. Derivative of 2x is 2. The derivative of negative e to the negative x is going to give me a positive e to the negative x. Okay. From here, if I plug in that negative infinity, I'm going to get essentially 2 over a positive infinity and 2 over a really, really, really big number, and gets close to 0. So our limit is equal to 0. Right, so so we used L'Hopital's, and then we used it again. Okay, let's look at our last example, number 8 here. So we've got the limit as x approaches 1 of the natural log of x minus x plus 1 over x squared minus 2x plus 1. Okay. So the limit as x approaches 1 of the natural log of x minus x plus 1. Okay. When I go through and I plug in 1 to that, we get 0. Okay. The natural log of 1 is 0. And then, so I get 0 minus 1 plus 1, so 0. Second one, the limit as x approaches 1 of x squared minus 2x plus 1. Okay, that also equals 0 because I'll show you in different color. We get 1 squared minus 2 times 1 plus 1. So 1 minus 2 plus 1 equals 0. I'm going to show you on this guy too. Right, so the natural log of 1 minus 1 plus 1 is 0. Okay, so now that we have that, we can use L'Hopital's rule. So the limit as x approaches 1 of the natural log of x minus x plus 1 all over x squared minus 2x plus 1 is going to equal the limit as x approaches 1. Now we start taking derivatives. Okay, so first our natural log of x, right? Its derivative is 1 over x. Next is that x piece. Derivative of x is 1, so it's going to be minus 1. And then we've got that plus 1 piece, which will be our 0, so I'm not going to write it out. Okay. Over. And then we look at that denominator. So that x squared becomes a 2x. And our minus 2x, let's change it to red. It's going to become a minus 2. All right, and then that plus 1, derivative is 0. So now we're looking at the limit of 1 over x minus x all over 2x minus 2. Okay. right? So we're kind of doing that thought process again. What happens if I plug in 1? Okay, well, 1 over 1 is 1, minus 1 is 0, and 2 times 1 minus 2 is also 0. So we're kind of stuck at that impasse again, where we're going to need to use L'Hopital's again. So the limit as x approaches 1 of my numerator, right, so that was 0, and the limit as x approaches 1 of my denominator, also a 0. So the limit as x approaches 1 of 1 over x minus 1 all over 2x minus 2 is equal to the limit as x approaches 1. Okay. Denominator is going to be the easier one to take our derivative of first. I get 2. Okay. Let's choose. I'll use this pink. Okay. For this piece right here, I'm going to look at it over here. 1 over x minus 1. I can rewrite that, right? That's the same thing as x to the negative 1 minus 1. That's going to help us take our derivative a little bit better. Okay. So when I take the derivative, right, x to the negative 1, so negative x to the negative 2, derivative of negative 1 is 0, right? So that means this is going to be negative x to the negative 2. Okay, ultimately we're plugging in 1, so we don't need to rewrite all of it, right? Because negative 1 to the negative 2 power over 2 is going to equal negative 1 halves. There we go. Okay, so once again, we used our L'Hopital's twice, right? There's our first time. There's our second time. Okay, and then we get our final answer here, right? But ultimately, I need all of that work, all that stuff that I wrote in my black here. Okay, that is all the stuff I need for this problem. Okay, the stuff I wrote in pinks, then that is essentially my like scratch work or my thought process. Okay, which is totally acceptable to do. We just got to make sure we have the other pieces also. Okay, so that's L'Hopital's.